Ankur Moitra from MIT, and he'll be telling us in his lecture series about recent advances in high-dimensional learning, kicking it off today with tensor decomposition. So go ahead, Ankur.
Great. So thanks, everyone, for coming, and thanks for the invitation to speak. So in the first part of this tutorial, I'd like to give you an introduction to one of the most important methods in high-dimensional parameter learning. These are tensor decompositions. So I'll walk you through what tensors are, what tensor decompositions do, and what problems they solve that ordinary matrix decomposition alone wouldn't do the job. And I'll talk about some candidate applications. So let's get started. So in fact, the story for tensor decompositions really starts way back when. It starts from the origins of factor analysis. So in case you don't know, factor analysis started in psychology with some pioneering work of Charles Spearman back in the early 1900s. And he had a simple hypothesis that's now called Spearman's hypothesis. He believed that fundamentally there were two types of intelligence, inductive and reproductive. So what these mean are that inductive is the ability to make sense out of complexity, and reproductive is the ability to store and reproduce information. So this was just a hypothesis. So how would you go about testing such a hypothesis? Well, here's the experiment that he devised. So he took 1,000 students and 10 different tests that they'd taken, and he recorded how well each student did on each test. So each row represents a test from a different subject, and each column represents a student. And then actually, in order to test this theory, he invented what's now called factor analysis. So roughly what he believed was that there was some nice factorization of this matrix M, this 10 by 1,000 matrix that he observed, into the product of two other matrices, A times B transpose. And what's important in here is actually the inner dimension in this factorization. So he believed that there was some way to approximately represent the matrix M as the product of two matrices, where A is a 10 by 2 matrix and B transpose is a 2 by 1,000 matrix. And in fact, what he believed was that the columns of A would represent something about which types of tests tested what elements of inductive versus reproductive reasoning, and each column in B transpose represents the aptitude of the student in inductive versus reproductive reasoning. So this is a hypothesis that you can try to test out, and he found some results that seem to support his conclusion. In fact, in psychology, people have continued to study this, and they've created a hierarchy of different notions of intelligence and how they relate through things like factor analysis. But in fact, if we think about this mathematically and as a learning problem, then something is a little bit strange about trying to find some unknown factorization that you think has a nice explanation just from a matrix of data. Because what he's really hoping is that maybe this matrix M, if there were no noise, you could write it as A times B transpose. And here I've written it as summation over I of AI tensor BI transpose. So the AIs are the columns of capital A, and the BIs are the columns of capital B. And basically, the question we're asking is one of identifiability. So even if Spearman was right, and even if there was no noise and we could observe this matrix M perfectly, and there was indeed some nice explanation of M as a product of A times B transpose, well, one question you can ask is, can we actually find this nice factorization uniquely? And actually, there's a major problem with trying to do factor analysis with just matrices, which is that even if there is a true factorization that's nice out there that lends itself to being interpreted very easily, well, you could take that factorization and you take any invertible matrix R, and you could put R times R inverse in between A and B transpose. And then when you group A times R together and R inverse times B transpose together, you get another perfectly valid alternative factorization. And the trouble is that that factorization is something that you might discover when you compute matrix decompositions on M. So even though there is a nice explanation for M in terms of factor analysis, you can't necessarily recover it uniquely. In fact, what I claim is that the answer to this question about when you can recover the factors A sub I and B sub I uniquely is actually not very interesting. You need very strong conditions on these factors in order to determine them just from M. In fact, what you need are things like the A and A sub i's and B sub i's being orthogonal, or you need that the rank of the matrix M is 1. And these are actually the only conditions under which you can recover these factors uniquely from a matrix. So this in-factor analysis is a major problem. It's called the rotation problem. You can take a valid factorization that you wanted to find and you can rotate it, and that might be the factorization you find, something that's not readily interpretable. So this is the way that I like to think about tensor methods, is that at their core, they're a way to solve the rotation problem. Because tensor methods, which I'm going to introduce in the next few slides, are things which are going to have unique decompositions under much tamer conditions. That's why people in diverse areas like psychometrics cared about them for many decades, but that's also why they show up in modern high-dimensional machine learning problems, especially ones in which you want provable guarantees. So now that I introduced the rotation problem, I want to tell you about something called Generic's algorithm. So first, we have the notion of a matrix decomposition that I described before. Is you can think about a traditional matrix decomposition as writing M as the sum of capital R rank 1 matrices. Each one of these rank 1 matrices is an outer product between an A sub I and a B sub I. Well, tensor decompositions look basically the same. You start off with a tensor, which now instead of a 2x2 grid of numbers instead of a 2-dimensional grid of numbers, it's a 3-dimensional grid of numbers. So you index into T with 3 entries, I, J, and K. Those are the indices. And the important thing is that you want to write this tensor of data as a low rank decomposition. And here, what's the notion of a rank 1 tensor? Well, if you give me a vector X, a vector Y, and a vector Z, you can similarly define their tensor product. And the entry in the IJK location of the rank 1 tensor, X tensor Y tensor Z, is the ith entry of X times the jth entry of Y times the kth entry of Z. So it's something that has this nice product structure. And when you have a tensor, what you want to do is you want to write it as the sum of not too many rank 1 tensors. That's what a tensor decomposition is. So now back to the original question about factor analysis, which I claim, one of the main reasons to care about tensor decomposition is the answer to the following question. So let's study, when are tensor decompositions unique? And there's a beautiful theorem of Generic in 1970, which says that suppose that the A sub i's and the B sub i's are linearly independent and no pair of vectors in C sub I is a scalar multiple of each other, then what you can do is if you have a tensor, which is the sum of not too many rank 1 terms, where each rank 1 term looks like AI, tensor BI, tensor CI, then what I claim is that that tensor decomposition is unique. So the uniqueness conditions we need are that the A sub i's are linearly independent, the B sub i's are linearly independent, and something on the C sub i's that's even a little bit weaker than linear independence. Now, uniqueness is a little bit subtle because you have to define it properly. You can never tell which of the rank 1 tensors in this decomposition is the first one, which one's the second one. So really what we mean is that it's unique up to permuting the rank 1 terms in this decomposition. And this also means that you can do things like you could rescale A sub I by some factor like 10, provided that you rescale B sub I by 1/10 or C sub I by something else, so that the overall scaling in front of the rank 1 term doesn't change. So this is a beautiful result of Generic from 1970. And actually, I have to confess that this result was not really understood. This result got rediscovered at least half a dozen times, maybe more at this point, by many different communities. So it's actually kind of interesting. I remember when I first started teaching a graduate course in high dimensional machine learning, I didn't even know about Generic's algorithm. I had some earlier reference that I thought was the original one that solved the tensor decomposition problem. And then I realized that it actually wasn't the first place where tensor decompositions had been defined. And so I did a bunch of reading to try and find this. In fact, this result of Generic actually appears in a paper of Harshman back in the 1970s. And I think, it's been rediscovered at least 6 to 10 times. And one of the beautiful things about Generic's theorem is that it turns out that it's actually an algorithm too. So sociologically, this is actually one of the reasons why it got rediscovered so many times, because in the psychometrics community, they had Generick's result. And then a few years later, they had an even stronger uniqueness theorem called Kruskal's theorem that turned out to not come with an algorithm. And afterwards, in the psychometrics community, people forgot about the fact that Generick's uniqueness theorem actually came with an algorithm, and they only knew about Kruskal. And that was actually one of the reasons why so many other communities seemed to rediscover this, was they all invented different algorithms, but I'll show you the original one today. So now the first thing that I want to do in this talk is I want to explain Generick's algorithm. It's beautifully simple, and it just relies on the notion of eigendecomposition and some simple operations that you can perform on tensors. So Generick's algorithm is a great way to get a feel for how exactly you can work with tensors. And then the later parts in this talk, I'll explain how exactly tensors come up in high dimensional learning problems. So in fact, tensors are very hard to work with. Most questions that you ask about tensors, like computing their rank, are computationally hard. So the trick behind Generick's algorithm is to reduce it to a problem about matrices, but it does it in a very delicate and interesting way. So imagine that we have this third order tensor, and it's third order because it's a three-dimensional grid of numbers. And one thing we can do is we can try and flatten it by adding up different matrix slices. So when I take this tensor T and I plug in a vector X, what I want to do is I want to add up the different slices through T, and I want to multiply each one of those slices by the scalar x of I. So when I do it in this way, when I hit the tensor T with this vector X, I end up with a matrix. So if the original tensor was n by n by n, X is an n-dimensional vector, and when I compute T of dot, comma, X, I get an n by n matrix that's defined through this formula. That's the first step in Generick's algorithm. And the important thing to think about what's going on here, and this will play a crucial role in understanding why Generick's algorithm works, is you should keep in mind just thinking about the world's simplest tensor when you're first seeing this algorithm. Think about a tensor that's rank 1. So what if the tensor that I was given were A, tensor B, tensor C? Then what happens when you hit the tensor with this vector X? What you're going to get is, again, going to be a matrix, but in fact, what's really nice is that it's a rank 1 matrix. In fact, you can express it in terms of A, B, and C. You get a scalar, which is the inner product between C and X, and then you get a rank 1 matrix, which is A, tensor B. So that's the key thing. So in fact, we don't know this underlying tensor decomposition for T. That's the thing that we'd like to compute. But we can express what doing this operation of hitting it with the vector X does to that decomposition that we want to find. Because this operation is linear, all it does is that same operation on each of the rank 1 pieces. So you get the sum over I of the inner product between Ci and X, that's a scalar, times AI tensor Bi. So if you start off with a rank R tensor, this operation of hitting it with a vector X produces a matrix whose rank is at most R as well. And here you should think about X as being chosen uniformly at random from the unit sphere. So now the way that I can think about this is that I can express it as the product of 3 matrices. So I can think about A times dx times B transpose, where dx is a diagonal matrix whose entries along the diagonal are the different inner products between C sub I and this vector X. And then I can do the same thing again with another vector Y. So I chose Y uniformly at random. When I flatten the tensor according to Y, I get A times dy times B transpose. So it looks almost the same. The only difference is that the diagonal matrix has changed depending on what vector I use to flatten it. And now here's the key idea in Generick's algorithm. So what if I take these 2 flattenings, one corresponding to X and one corresponding to Y, and then I create some new matrix that looks like the flattening I get from X times the inverse of the flattening that I get from Y. Now, just to keep things simple, I'm going to assume that all of these matrices are invertible. But really, when they're not invertible, what you would do is you would use the pseudo-inverse instead. That's not a major complication, but it just means that I have to use pseudo-inverses. So let's keep it simple and let's assume they're invertible. Now, the key thing is that I can express what this matrix T of X times T of Y inverse looks like in terms of the factors that I want to find. And so if I just write down what that expression is, it's A times dx times B transpose times B transpose inverse times dy inverse times A inverse. So now the B transpose cancels with the B transpose inverse, and I get something really nice, which is A times the diagonal matrix times A inverse. And this is the aha moment, because when I only give you access to T, you can compute T of X, you can compute T of Y, and you can compute this T of X times the inverse of T of Y. That matrix that you've constructed from your data now has a simple diagonalization, because what this really is it's an eigendecomposition. So if I can compute the eigendecomposition of this matrix that I've constructed in the third step, then it's actually going to reveal some of the factors that I wanted to learn, because I'm going to learn A as the matrix that I need to diagonalize that matrix that I've constructed. And so the key claim is that, if your factors C sub I had the property that no two of them were scalar multiples of each other, then you can check that, when you compute these flattenings, T of X times T of Y, and create this new matrix, that actually this eigendecomposition will not only be an eigendecomposition, but it'll actually be unique. And that's what guarantees you to actually find the true A that you wanted to find. So that's only part of the factors, because I still need to find the columns of B, and I still need to find the columns of C. So what do I do after that? Well, I can diagonalize a matrix that's the other way around. I take T of Y times the inverse of T of X, and that's going to have another nice expression in which the thing which diagonalizes it is B. And when you've learned all of the factors A sub I and B sub I, it turns out that you can match them up, because the eigenvalues that these eigenvectors correspond to, they turn out to be reciprocals of one another. And then there's a way, once you know the A sub I's and B sub I's, well, the only unknowns you're left with are the C sub I's, so you can just solve a linear system to recover them. So this was Jenrick's algorithm. It's amazing that he came up with this way back when in the 1970s. And it's something which was actually done within the psychometrics community. And even though they didn't have the language of algorithms, because this actually predates a lot of theoretical computer science, they still had very interesting algorithms in this literature. So now let's go back to our rotation problem. So the real problem with matrix decompositions, as I mentioned, was that the factors A sub I and B sub I are not uniquely determined when all you know is the matrix. But what happens if you give me a low-ranked tensor, where T is the sum over I of AI, tensor BI, tensor CI? Well, we can ask the same question, which is, when can we find the factors A sub I and B sub I uniquely? And the answer now is much broader. We need a much less restrictive assumption on the factors in order to be able to do this. Because what Jenrick's algorithm tells us is that we can uniquely recover these factors up to some naive rescalings, provided that the A sub I's and B sub I's are full rank, and that no pair of vectors in the C sub I's are scalar multiples of each other. So this very simple algorithm turns out to be immensely powerful within high-dimensional learning and high-dimensional statistics. So now that I've introduced the rotation problem and Jenrick's algorithm, let's have some fun with some applications. So really, what Jenrick's algorithm is good for is it lets you solve all kinds of learning problems in latent variable models. Let me explain some actual applications so we can get a feel about when we can apply Jenrick's algorithm and what kind of structure in our probabilistic models is conducive to being able to use tensor methods in the first place. So let me tell you one which I think is another beautiful story. It's about phylogenetic reconstruction. So here in phylogenetic reconstruction, we have this notion of different species and how they evolved from each other. And just to introduce some terminology, we have some species that are currently living today. These are called extant species. These are the red circles. And we have some species that are now extinct. And these are the green circles. And basically what we believe is that there's a tree of life that explains how the different species evolved from each other and how those relate to species that are now extinct but only existed in the past. Now, one of the basic goals in phylogenetic reconstruction is we have access to genetic sequences from modern living species, all of these extant species, and we want to stitch together that information as a way to piece together what this tree of life looks like. So that's the basic inference task in phylogenetic reconstruction, is that you have genetic information and you'd like to find this underlying generative model that explains how your data was constructed. Now, for those of you who care about the applications, let me say a few words. Really, what you assume is that for all of the living species that you've already solved the very challenging task of aligning their sequences. So when you think about having all of these different species and you've aligned their sequences, you think about looking at the jth coordinate into this vector of base pairs that describes, the order of base pairs in each of their gene sequences. And you think about that as being a sample from your model, because each one of these species, well, it'll have a symbol at that particular genetic location in its DNA. It could be something like A, C, T, or G, or it could be something even more complicated depending on how you set it up. But the way that this works in terms of a stochastic model is that you assume that there's some alphabet sigma. And this could be, a size 4 alphabet like A, C, T, and G. It could be something bigger like, the set of all proteins. You get to pick it. But what you assume is that there's some underlying distribution on the root. So you first choose what symbol is assigned to the root. And then what you do is there are a bunch of transition matrices that describes how the symbol for a parent affects the distribution for the symbol of its child. So this matrix RZB describes, if the alphabet is size K, it's a K by K matrix. And one of the rows in it describes, well, if this hidden node Z has a particular symbol in the alphabet, what is the conditional distribution on what symbol is assigned to its child, namely the species that's described by B. So this is a model that describes the transmission and things like mutation along this tree of life. And the question is, well, can we actually reconstruct this underlying tree and these transition matrices that describe these conditional distributions when all we get to do is push a button and get a sample? And each sample here, just to be precise, is really just a vector of symbols. The length of this vector represents the number of extant species, and that vector just describes which symbol we observe at each of the different leaf nodes in this tree. Now, actually, there are related problems that fit exactly into this framework too. For those of you who are more familiar with, things like signal processing and speech recognition, well, a very specialized case of this is already the hidden Markov model, which you can think about as being a situation in which the tree structure that describes your generative model is very simple because it's just this caterpillar graph. There's just a line on these hidden nodes, which represent hidden states in your system. And what happens is that at each node, you have a hidden symbol that you don't observe. And then you have some matrix. So first you choose an initial distribution on the first state, which just when you push the button chooses what symbol you assign to the starting state X. And then you look at these observed matrices, observation matrices that describe for each hidden state, what is the distribution on the symbols that you observe at that time step. And then there's a bunch of transition matrices that describe, well, once you tell me the state at X, how does that affect the distribution on the state at Y? So this is what a hidden Markov model is. It's just a special case of one of these phylogenetic tree models where you have a very simple underlying tree. And so we can ask this question in the context of phylogenetic reconstruction, which is a deep and beautiful question that connects to a lot of mathematical biology and statistics, which is, can we reconstruct the topology from random samples? So usually what you do is you assume that all of these transition matrices in the phylogenetic model are full rank so that you can reroute the tree arbitrarily however you want. And then it turns out that if you think about it, different nodes which are observed, well, the further nodes are apart from each other, the closer and closer to being independent they ought to be, because you have to go along a long path to get from X to Y. So it turns out that you can actually make this intuition precise And there's actually a distance function along the edges that if you told me the transition probabilities, the transition matrices, and you told me the underlying tree topology, there is this crazy expression right here that describes a distance function between pairs of edges. And the key thing is that you can actually estimate this distance between pairs of leaves. And the distance between leaves turns out to be the sum of distances along the paths in the tree. This was completely a non-obvious result. It's a beautiful result of Steele from the mid-90s, because the way that I've described it right now, it's not even obvious that the thing is non-negative to begin with. So it turns out what you can do is you can just use Steele's distance function to reconstruct the topology of the tree. Because imagine that I have 4 different leaves, A, B, C, and D. Well, you can think about how to connect all of these 4 different leaves with paths to each other through the tree. And you can convince yourself that there's some basic topologies that can happen. Because what can happen is if you look at the least common ancestor as A and D, well, that might be something that separates A and D from B and C. And similarly, the least common ancestor of B and C, that node in the tree might separate those 2 nodes from A and D. So the important thing is that you can actually query this distance function to determine which of these quartets is actually the correct induced topology on these 4 different leaves. And it turns out that you can use this to actually reconstruct the topology of the tree of life. So now we actually get back to tensor decomposition. This was a little bit of an aside, but now that we can assume that we know what the underlying topology of the tree looks like, the basic question we want to solve is, how can we actually construct these transition matrices along the trees? And it turns out this is one of the earliest places where Jenrick's algorithm was rediscovered. It was discovered by Chang in the context of mathematical biology. So a bunch of statistics literature actually, I remember seeing that it all quotes Chang's lemma as being the origin of tensor decompositions. It turns out that it was known even before that. And then it turns out that even those earlier results of Lurgans, Ross, and Abel turn out to be rediscoveries of a paper of Harshman, who in turn quotes Jenrick. So it's quite a convoluted story that I would need quite a complicated graph to describe the topology of who rediscovered what. But in any case, what Chang's lemma does is really it invokes Jenrick's algorithm in a clever way. So here's the basic idea, is that, imagine that we know the tree topology right now. And all we want to do is we want to reconstruct what are these transition matrices along this phylogenetic tree. So here's the beautiful idea about how to apply Jenrick's algorithm is, let's say that we take 3 different leaves, A, B, and C. What we can do is we can find an internal node Z. Now, in the context of phylogenetic reconstruction, this is an extinct species, so we have no information about it. It's a purely latent variable model. We can't figure out what this latent variable model is set to in our different samples. But now what we can do is, because we can reroute the tree arbitrarily, let's imagine that Z was now the root of the tree. Because what that means is that we can now describe paths that go from Z to A, and Z to B, and Z to C. And the key fact about these paths that you can see from this figure is that these paths don't intersect each other. They're completely edge disjoint. And what this really means is that you can think about it like a much simpler diagram where you have this very simple tree. You have a hidden node Z, that's your latent variable model. You don't know what symbol of the alphabet it's assigned in your samples. All you observe are the symbols that are assigned to A, B, and C. And there's some stochastic matrices that describe how you get from Z to A, how you get from Z to B, and how you get from Z to C. But here's the really important fact, and this is the key to how you use tensor decompositions in learning problems, is the key fact is that the joint distribution on A, B, and C is very complicated, but the distribution of A, B, and C are conditionally independent if you condition on this latent variable Z. So what I can do is I can sum over all of the symbols in this alphabet. I sum over all choices of little sigma. I multiply by this probability that Z is assigned to that symbol in the alphabet. And then I look at a vector right here, which is the conditional distribution of what the symbol that's assigned to A is, conditioned on Z being assigned to the symbol sigma. So if my entire alphabet is size k, there are k different possibilities, then this vector of probabilities is a length k vector. And the important thing is that A is conditionally independent on B and C. So if you look at the joint distribution on A, B, and C, it's actually a rank 1 tensor once you condition on Z being equal to sigma. Because the joint distribution on A, B, and C conditioned on Z equals sigma is the tensor product of the conditional distribution on A times the conditional distribution on B times the conditional distribution on C. So this is actually the first aha moment, is that, it sounded, when I first introduced like tensors, it sounded like, well, here's a notion of rank that generalizes what happens for matrices, but where in the world would this come up in problems that I actually care about? Well, the truth is that a lot of times when you're working with nice probabilistic generative models, you actually do have some nice conditional independence structure. And that's exactly what happens here in phylogenetic reconstruction and in hidden Markov models, is that you have some conditional independence on your latent variables. So the important thing here is that if you think about the way that this problem is set up, well, what I'm describing is the joint distribution over A, B, and C. That's a k by k by k tensor. And that's something that I can now estimate from my data. So I can compute what this tensor is, and then I can compute its tensor decomposition. And that's unique under pretty general conditions. You just need that these guys are all linearly independent, which happens in a lot of models. And then you can actually uniquely recover what these conditional independent distributions are, which actually describe the transition rules of how you get from Z to A, Z to B, and Z to C. So this is a result of Mossel and Rock. Interestingly, I feel like everything in this literature ends up getting rediscovered. Mossel and Rock discovered this in the context of phylogenetic reconstruction back in 2006. It turns out, about 8 to 10 years later, people were still rediscovering using tensor methods in much simpler things like learning hidden Markov models, which are really the simpler problem when you know the underlying tree structure. But part of the reason I wanted to give a tutorial on this is to try and explain some of the historical quirks and how at least I think about the relationship between these results. So what they showed was that there's a polynomial time algorithm to learn a phylogenetic tree. Now you have to be careful because sometimes when you have long branches, you can't really reconstruct the transition matrices exactly. But what you can do instead is you can reconstruct other transition matrices that are statistically indistinguishable from the ones that you actually want to learn. And that's how they set up the problem, is what's called pack learning. In fact, what's kind of neat is that you can ask questions like, well, when we think about Generic's algorithm, we needed this uniqueness. We needed these assumptions on the underlying factors, that the factors were linearly independent. Now you could wonder, do you really need those kinds of assumptions to solve these tensor decomposition and parameter learning kinds of problems? Or is it an artifice of the algorithms that we have for solving these problems? Well, it turns out that it really is necessary. There's another beautiful result contained in the Mossel and Rock paper, is it turns out it's computationally hard to learn the parameters of even a very simple general hidden Markov model when your transition matrices are not full rank. It turns out that it's related to a problem called noisy parity, which is an infamous problem in computational learning theory that people now use to build crypto systems based on. So this really is hard when you try and weaken these uniqueness assumptions that we started off with. And it's part of the reason why some of the later generalizations in the psychometrics literature of Generic's algorithm ended up not leading to computationally efficient algorithms, is that they actually weaken the assumptions you place on the factors in a way that those problems might genuinely be computationally hard. Okay, so now what I'd like to do is I'd like to take a step back, because I think what's important in all of this is to really understand what tensors are, how they arise in high dimensional learning problems, in particular, why you're naturally faced with low dimensional tensors in learning problems, and to try and abstract what it is that makes tensor methods amenable to those kinds of problems. Because if you think about phylogenetic trees and hidden Markov models, I claim what's really happening, what makes the thing work, why you have a low rank tensor, is because there's conditional independence. This is what I'll call the power of conditional independence, is that's the way in which you find a low-rank tensor within the statistics which you can compute from your data. So in phylogenetic trees, what does this conditional independence look like? Well, it looks like when you have 3 different leaves, A, B, and C, those are your extant species. You have a latent variable model that describes an extinct species, and the distribution on the extant species is conditionally independent given the extinct one. So hopefully extinct comes across in my microphone. I have a new microphone, so hopefully it's not all muddled together. Let me tell you one more simple application of tensor methods. That's one of the beauties of these algorithms, is that once you have this tool, you can actually just go around looking for learning problems, figure out where you have nice conditional independence properties, and just use tensor decomposition results. That's it. It becomes very formulaic, and you get a long list of applications just from this one Generics algorithm. So let me tell you about another problem. I think it's another simple problem where you can think about how to use tensor structure. It's a problem that's near and dear to my heart because I've worked a lot on these kinds of things. It's about learning mixture models, specifically mixtures of Gaussians. In fact, you make a kind of strong assumption about the components of the Gaussians in this case, which is you assume that they're all identical spherical Gaussians. So let's imagine that we get samples from the following generative model. So first, we have a high-dimensional Gaussian, which has a mean mu, and a covariance, which is sigma squared times the identity. Now, what that means is that all of the different directions in the standard axis-aligned directions are all independent of each other. It's a spherical Gaussian in terms of its shape. And what you do is you create a mixture model out of these things. So you have not just one Gaussian, but you have k Gaussians. And the way that you sample from the model is you choose one of the components at random with probability proportional to W sub I, that's your mixture model. And then once you've chosen which component you're sampling from, you just take a sample from the underlying Gaussian. In fact, each of these Gaussians has a different mean mu sub I, but they have the same covariance, which is sigma squared times the identity. So just so that we're all on the same page, this is another example of a latent variable model. What is the latent variable? Is that what I observe is I observe a high-dimensional sample from this distribution, but I don't know which component generated it. That's the latent variable, and it's again a discrete latent variable because it just takes on one of k different values describing which of the k components the sample came from. So now the basic task here is I want to take a bunch of samples and I want to learn the underlying parameters, the W sub i's and the mu sub i's. Let's assume sigma squared is known just for simplicity, not a big deal if it's not. And I'd like not only a statistically efficient method that takes only a polynomial number of samples to get to some desired accuracy, but in fact, I want my estimator to be efficiently computable too. And it turns out that tensors are a great way to do that because we have Generics algorithm. So the basic question here is, can we reconstruct the underlying parameters in polynomial time? So let me tell you a result about of Sue and Kakaday, which is that there's an algorithm that works via tensor decompositions that has polynomial runtime and sample complexity. And it works just under the conditions that the mu sub i's have full rank, and actually that the W sub i's are all non-zero. So these are very tame conditions. Now, just to be precise, in fact, what happens when you're really close to the mu i's being degenerate? Well, your running time and your sample complexity blow up. So what really happens is that you create a matrix whose columns are the mu sub i's, and you look at the smallest singular value of that matrix. That describes how far you are from being degenerate. And the running time and the sample complexity depend on 1 over sigma min. This is a more sophisticated point, so don't worry about it. Let's just assume the mu sub i's have full rank and see what happens. And we won't worry exactly about the sample complexity issues, but these are issues you have to deal with. So here's the main lemma. In fact, you can reprove the result just with a couple line proof once you have Generics algorithm. It's very simple. Here's the key lemma. This is all that there is that it turns out what you do is there's a tensor that we want. This tensor would have a low rank decomposition, which determines the parameters that we want to learn. So consider this tensor T, which is the sum over I of W sub I, that's the scalar mixing weight, times mu sub I, tensor mu sub I, tensor mu sub I. That's an order 3 tensor. Its rank at most k. Now, we don't directly have access to this tensor. That would be nice if we did. It turns out that what you can do is you can compute the first, second, and third moments of your distribution. And you can do that just through samples. And you can construct this tensor T based on the empirical moments from your distribution. And then all we'd have to do is we could apply Jenrick's algorithm. So, the main abstraction is actually literally the same thing. Because the way that we're using tensor methods is we're showing that there is a low-ranked tensor that we can compute based on samples from our model, whose tensor decomposition reveals the parameters we want to learn. And just to emphasize, what's really important in this is, again, the uniqueness result behind Jenrick's algorithm. Because we need that not only can we compute this tensor that is low rank, whose ideal low rank decomposition gives us what we want to learn, we need to know that when we compute any other low rank tensor decomposition, that we really do get something that looks like this and learns the parameters we're after. So that's why uniqueness is important. And that's why tensors play a key role and solve some of the learning problems and identifiability problems that just having access to a single matrix, like just second moments of your distribution, sometimes just doesn't cut it. Okay, so there's a question from the audience. Let me just answer this live. So am I saying that 3 tensors is enough? No need to do 4 tensors or higher? Great question. So what I'm actually saying is that for a bunch of these problems, like learning mixtures of spherical Gaussians, like phylogenetic reconstruction, like hidden Markov models, 3rd order tensors work. But you're exactly right. You're foreshadowing the fact that there's a lot of power to going to higher order tensors. And in fact, there are many more sophisticated algorithms that I'm not going to get into here or in this tutorial that work based on going to higher order tensors. And there's a lot of value to doing that because you can handle more components. You can learn more sophisticated models where you don't assume things like spherical Gaussians, but that's a much more sophisticated topic. So it's a great question, but I can only partially answer it. All right, so let's continue. So let me prove this lemma. This lemma is super easy to prove, right? So what am I going to do? I'm going to do the only thing I can do. I'm going to compute the 3rd order moments for my distribution. Okay, and so what are the 3rd order moments? Well, I look at my random variable x, which is a d-dimensional vector, and I look at the ath coordinate in it, and I multiply it by the bth coordinate, and I multiply it by the cth coordinate. So I look at the expectation of x of a times x of b times x of c. Nothing complicated going on here. And if you think about it, what's really going on is you're computing a 3rd moment tensor, which is the expectation of x, tensor x, tensor x. That's a d by d by d tensor. But I'm looking at the entry in that tensor that's in location a, comma b, comma c. Now, the important thing is that you can think about a mixture of spherical Gaussians in the following model. So first, you choose a random variable which describes which component you're sampling from. And when you choose that component, you really fix the vector to be mu sub I, because that's the center of that Gaussian. And then you add independent noise. You add a spherical additive Gaussian noise to that component. Now, the key thing about mixtures of spherical Gaussians with identical components is that the additive noise is independent of which of the centers you choose. So in fact, what's really nice is that when A, B, and C are distinct, the 3rd moments of your sample of mixtures of Gaussians look the same as the 3rd moments of the distribution where you merely sample the center and add no noise. And of course, no noise is a lot easier. So in fact, what it looks like is it looks like the sum over I of W sub I times mu I, tensor mu I, tensor mu I. That's a d by d by d tensor. And you index into it at the A, B, and C location. So if A, B, and C are distinct, that's your expression. So how do you compute this 3rd order moment and get a corresponding entry in T, which is what you're after? They're the same thing. Something slightly fancier happens when you have repeated indices. So what if A equals B? So you're really computing expectation as XA squared times XC. So you get the same thing where you index into this ABC entry of this low rank tensor you wish you had. But there's an extra factor that comes from the noise, this additive sigma squared noise. So you get a plus sigma squared times the sum over I of W sub I and U sub I times C. So this just comes from expressing what the second moment of a Gaussian is. You can just read this off Wikipedia and compute this expression, very simple. Now, the key thing is that this is not the thing that I'm after, because it's not the ABC entry in T. But if I know sigma squared, then I can actually remove this extra factor and subtract off something to correct the moment so that I really do get the ABC entry of T, because this is really just sigma squared times the first moment of the distribution. I can compute the first moment. So the same thing happens when A equals B equals C. It's just a different correction term. So it's minus 3 times sigma squared times, again, the first moment. And that's the proof, right? So we're actually done. This is the algorithm for learning mixtures of spherical Gaussians. This is literally all you need to do to get the algorithm. In fact, you can write the tensor T if you want as a little bit more compactly. What it actually looks like is if you look at the third order tensor and you do this correction term, and there's a nice way to interpret what the corrections look like through something called isoteralism theorem, which has to do with relationships between the moments of Gaussians and matchings, but whatever. I don't expect you to understand that. But the key point is that now when you compute this tensor T, you can just use Generic's algorithm. That's it. That's the learning algorithm. So this is the power of conditional independence. We get an algorithm for learning mixtures of spherical Gaussians, and it just works. You can also talk about other generative models, other latent variable models. There's a really nice one that I've also worked on called topic models, where you think about the following type of generative model. You're observing documents, which themselves are bag of words, which words show up in those documents. And the way that you think about these documents as being constructed is that there's some underlying set of topics, and each topic is a distribution on words. And what you do is each time you generate a document, you choose one of the topics at random. And then once you've chosen the topic, you sample words from that corresponding distribution on words, and that's your bag of words that you get in your document. So the important thing is that topic models also have great conditional independence structure. What is the conditional independence? Is you condition on the latent variable of what the hidden topic is for a given document. In fact, this even works with so-called mixed models, where documents are actually a mixture of topics. And there are things called the latent Dirichlet allocation model. And again, you can use tensor methods, because the tensor you construct is also based on third order moments. In this case, it's the joint distribution on the first 3 words in your document. You can even do it for things like community detection, where I won't get into this, but it turns out that when you generate a random graph with a planted community structure, if this community is better connected within itself to the rest of the communities, when you do it through something called the stochastic block model, there's a way to count different graph theoretic substructures, in this case, counting 3 stars, that actually have nice conditional independence properties in what the expected counts are. And then you can, again, just use Generic's algorithm. In fact, it even works for mixed models with community detection, which are so-called mixed membership models. But, I also want to, in the last couple minutes, I want to disabuse you of the idea that all of this stuff is really well solved. So far what I did was I went back to the 1900s and talked about factor analysis. Then I talked about Generic's algorithm, which got rediscovered many times. And I showed you how it just nails one by one these different types of latent variable models when you have a conditional independent structure. And there's a lot more in this literature where the conditional independent structure takes a lot more tensor theoretic insights to figure out how to work with. But what I want to do is I want to give you a hint of, actually a whole world out there where things are way more complicated, where I don't really have any answers. And, this is more of an invitation. Please solve my problems. So let me tell you about another kind of latent variable model, which is called orbit retrieval. Now, something funny is going to happen in this kind of latent variable model, which is that instead of having the latent variable models being discrete, like in the case of phylogenetic reconstruction, where they're a hidden symbol, or mixture models, where they're what component was used to generate the sample, they're actually going to be continuous. And that's pretty nasty. But the only way that we're going to do with continuous latent variable models is when they have a group structure. So what happens if we want to learn the parameters of a generative model with a continuous latent variable? Let me give you an example. So one example of a problem that fits into the class of things called orbit retrieval is imagine that we have a periodic signal, but what happens is that we get the signal plus noise, but with a random shift, where the offset is chosen uniformly between 0 and 1. So it's a continuous shift. So our latent variable model is that when we observe a noisy sample, we don't know what that shift is. So it's a continuous latent variable model. This is a very important problem in signal processing. There's something called global registration, where you get noisy pictures of a two-dimensional image, but now what you don't know is the rotation within SO2. These are noisy pictures of Alan Turing, and we don't know what the group element of SO2 is that describes how we've rotated the picture of Alan Turing. And in fact, these problems go pretty deep into really some of the fundamental areas in the sciences and engineering, where there have been major discoveries with tons of Nobel Prizes. One of my favorite examples is what's called cryo-EM microscopy, where we want to determine a 3D molecular structure from random 2D noisy projections. And here, the underlying thing is that I have a 3D structure I want to reconstruct, but I don't actually know what rotation in SO3 it is. So the way that you formulate orbit retrieval problems is that there's an underlying group and a group action, and there's an underlying signal that you want to recover X. So what happens is each sample looks like you choose a random element of your group from the Haar measure, you apply that group action on X, and then you add noise, let's say Gaussian noise. And the question is that you want to recover the underlying vector X. Now, you can't actually tell the difference between X and anything else in its orbit. So instead, what you want to do is you want to recover some X hat that's close to the orbit. That's why it's called orbit retrieval. And so this leads to something that I call orbit tensor decomposition. Because in this case, what you can do is you can do the usual thing. You take samples from your model and you compute the moments. Now the moments also have a tensor structure. But the difference is that it's not a discrete sum over some discrete latent variable. Instead, it's an integral over this continuous group, because it looks like rho of G times action on X, tensor to the third power. So the question is, can you recover X up to its orbit from a tensor that looks like this? Now it's kind of problematic because T is actually not low rank. You actually have to use the algebraic and group theoretic relationship between the different factors in order to solve the decomposition problem. Let me tell you a baby result. This is all that I know, is there's a polynomial time algorithm that works when X is random, when you have the continuous group SO2. But really, there are many bigger problems out there, like what happens for non-abelian groups? Well, the truth is we probably need some representation theory, and this is a bit beyond my knowledge of Clebsch-Gordon coefficients. I'll give you just a little baby hint in the last 1 or 2 minutes about what goes into this algorithm, is that there are different ways you can think about working with tensors. There's a beautiful way called tensor networks, which are graphical representations for tensors and operations on them. So you think about a tensor, like this little diagram on the left. There's just a T sitting in the middle, and there are 3 legs. And there are 3 legs because you have to index in with 3 different choices of, one of I, one of J, one of K, to figure out what the corresponding entry of T is. Now, the important thing is you can manipulate these diagrams as a proxy for doing tensor manipulations. So when you take 2 different third-order tensors and you connect them along some leg, well, the resulting thing you look at has 4 different legs outgoing, so it looks like a 4th-order tensor. And in fact, what you're doing, or you're supposed to be doing, is you're supposed to be associating I and I in these tensors T and U, and then summing over it to get a 4th-order tensor that's indexed by A, B, C, and D. But now the cool thing is that you can actually build a lot of beautiful algorithms from simple tensor networks. In fact, in the existing literature that does a lot of things with tensor methods for all kinds of latent variable models, a lot of times these are implicit within their work, is that the way that they're using spectral methods is they're really building them from tensor networks. But it turns out that you can define a general blueprint for how to use a tensor network. If I give you a tensor T, you use this tensor network to create a new metatensor, and then you flatten it somehow into a matrix, kind of like the way that we flattened to get Generick's algorithm. And then you do something spectral. You compute the leading eigenvector. But what you can prove is that a lot of times that actually recovers the underlying X that you want. So what's kind of crazy is that we tried this framework of, how do we get orbit tensor decomposition? for this case of SO2. And this was the blueprint we came up with. It's a spectral method that's so ugly, you would never write it out if you had to write out all of these indices by hand and explain this formula. But this is the blueprint. And kind of amazingly, you can show that this is literally the smallest tensor network that will work for this problem. So there's a whole rich world out there about how exactly to use tensors now in the context of having group structure. All right, so at the beginning, I didn't really give you an outline of what I'm going to talk about in this tutorial, but part one was about some of the bread and butter of how do you do high dimensional learning. And one of the most powerful tools we have are tensor decompositions and their uniqueness that paves the way for applying them for latent variable models. What I'll talk about next time are algorithms for robust estimation. And these are unsupervised learning problems where we're going to start to tease apart, how do you get provably robust and computationally efficient algorithms, even in cases where your moments don't actually have a nice tensor structure? What happens if an adversary is corrupting 10% of your data? It turns out there's still a lot you can do algorithmically. Then I'll talk about the difficulty of supervised learning in the context of noise, because there it turns out that there's an interesting chicken and egg problem of finding the right noise model that's both reasonable and lends itself to algorithms rather than computational intractability. I'll pontificate wildly on what these things might have to do with algorithmic fairness, because it's interesting to me that that a lot of problems in algorithmic fairness seem to be, you could frame them as learning problems in some regimes. So I think there might be more to do there. And in the last part, I'm going to go really outside the box, and I'm going to say that actually, latent variable models are much more general than we give them credit for. There's a sense in which inverse problems you want to solve in the sciences that you need to do in order to answer scientific questions, like, is this thing I'm observing in the sky a double star or a single star? Well, you can think about those inverse problems as a type of latent variable model for which a lot of the techniques that I'll be describing will actually have some interesting things to say. So I'll stop there and see you next time.
All right, thanks so much, Ankur, for that great talk. I think we have time for a couple of questions if people want to ask.
Maybe I can ask a question. So Genric's algorithm, the tensor has to be of rank at most n, I guess, where is there some simple modification of it that does well for slightly above n?
No, that's a great question. So, I mean, there are a few different answers for this, I think. So first, you can do something at a very extreme end, which is, let's say you have a third order tensor, and the factors x aren't merely generic, but they're actually random. Then you can do way better because you can actually recover the underlying factors through sum of squares and other kinds of methods up to n to the 3/2. Now, what's kind of wacky is that, under generic assumptions, not actually random x, these tensors are unique up to about n squared. And we can't get anywhere close to n squared. In fact, Kruskal's uniqueness theorem, the important thing is that it would work up to 3/2 times n. But it's not known computationally how to actually solve the corresponding algorithmic problem underneath Kruskal's uniqueness theorem. So in the case where you have generic tensors, nothing is yet known about how to go above n. In fact, what's kind of a killer is that you can think about methods in algebraic circuit complexity that, there's this beautiful result of Ron Raz that if you can construct explicit third order tensors of rank little omega of n, then you would get the first superlinear circuit lower bounds. Now, unfortunately, that tells you, some of the difficulties about trying to get algorithms that, work generically beyond n, like n log n, is that how are you going to actually certify what their rank is, when you go up to n log n without accidentally proving some pretty earth-shattering results in circuit complexity. In fact, what's a little bit worse is that people have been talking about algebraic obstructions to the methods that we have, like the method of shifted partial derivatives in algebraic circuit complexity. These turn out to give you no-go theorems for getting beyond 8n with different types of formulations. for third-order tensor decompositions. But then again, the answer to your question is morally kind of yes, because there's something trivial I can do, which is I could take a fifth-order tensor and I could massage it into an n squared by n squared by n tensor. And then generically, you're going to have linear independence even up to rank n squared. So that you can actually start to study through models of like smooth analysis and study their stability, and people do that. I've done that. It turns out that you can even do a little bit better, which is for fourth-order tensors. There's actually an electrical engineering community that has to do with independent component analysis that has uniqueness theorems that work up to n squared. So there's sort of a very interesting, relationship between what you can and can't do. But if you think about learning context, what it costs you to work with lower-order tensors is merely what it costs you to work with higher-order tensors is that you have to take more samples in order to reasonably estimate the entries. And so, for example, for orbit tensor decomposition, take the order of the tensor to be 100. It should make the problem a lot easier. I don't know anything.
Any more questions?
Are there questions on the Q&A? Oh, okay. Sorry. Let me just answer live some of the questions that are asked on the Q&A. So there's a great question from Holden Lee. How robust is Generic's algorithm to noise? So what really plays the key role here is robustness to noise of an eigen decomposition. So it turns out that this will be robust to noise provided that the eigen values are separated from each other and that the actual matrix that you use to diagonalize it is well conditioned. So in my book, which is linked to on the Simons website, I think, there is a noise stability analysis there, but unfortunately, I don't actually know of earlier noise stability analyses. Some of the first applications of tensor methods in learning problems didn't actually use the phrase Generic's algorithm. So they actually invented their own versions of noise stability analysis for their particular problems at hand, but it is stable under fairly reasonable conditions. And is there any connection between tensor decomposition and deep learning? Sort of. So there's a bunch of work that Teng-Yu Ma and collaborators have where you think about, even depth 2 nets, thinking about the joint distribution you observe on the output. And you can think about the sense in which it's approximately low rank. This also shows up even in situations where you have like directed graphical models, but I can't say too much more about that because it's very technically complicated and I don't know.
Okay, so I actually am having some technical difficulties and I can't see questions in the Q&A, but I assume there aren't any more of those. So thanks again, Ankur, for the fantastic talk. Looking forward to the installment tomorrow. And let's take a break in the Gather Town until noon when we'll have another talk from Jelani.